name is Azam Isam. I'm from Iraq. I'm a master degree in Istanbul Okan University, Advanced Electronics and Communication Technologies. My paper is energy efficient by reducing interference in wireless sensor network using the OFDM modulation technology with 2.4 and 5.8 gigahertz frequencies. Content or what we did. We are modeling wireless sensor network in smart home using a 3D ray tracing program in the MATLAB. Other steps, next steps, calculating the RSSI value for all transmitters inside home. Third steps, we finding SINR due to all transmitters. Fourth steps, using the OFDM to improve value abstract. Smart home of the future will contain many wireless sensor network. Energy efficiency in wireless communication is one of the biggest problem in the sensor networks. Increasing efficiency will increase lifetime of sensor device and reduce interference. This paper models the interference in smart home network, the received signal strength information, RSSI reading at each location in the building is calculated using the ray tracing software in MATLAB, and this data is used to interfere the signal to interference noise ratio SINR in the area covered by the network. Feature of the IEEE 802.11n protocol and OFDM are proposed to increase SINR in the network. The paper also compares the effect of using different 802.11 spectrum bands, 2.4 gigahertz or 5.8 gigahertz on the performance of the network. Here we have the location of transmitters. We have one the main transmitters in the middle of house, and 100 transmitter, 100 interfering transmitters in the other places in the home. This is OFDM generation block. OFDM contains many steps. Some of them in the transmitter and others in the receivers. Serial to parallel and symbol mapping, inverse fast Fourier transform, and added cyclic prefix. Parallel to series, all those in the transmitters. And after that we have fading channels. After that we have serial to parallel. From here we have in the receiver we have serial to parallel remove. We remove cyclic prefix and fast Fourier transform and sample unmapping and parallel to serial conversion and information to on sync in the receiver. Here the signal to interference and noise ratio SINR at the receiver node. The signal to interference and noise ratio, we have SINR. We have SINR equal PU over noise plus summation of PW over DW from W to V, where PU is the transmitter power of the node U, is the main transmitter in the middle of house. DU to V is the distance between transmitter node from node U to receiver node V. Alpha is the path loss coefficient. Noise is the adductive wide Gauss noise power. PW is the transmitter power of the some node W, which is not node U transmitting on the same carrier. Here we have RSSI inside home at 2.4 frequency, at 2.4 giga frequency. We have here we have a transmitter in the middle of house and RSSI everywhere in the house. Here we calculate SINR inside home at 2.4 gigahertz, and we can see SINR is higher when it's red and orange, and it's small when it's blue. Here we have a comparison between 5.8 gigahertz and 2.4 gigahertz, and you can see. It's not a huge difference between them and inside house. When which green, it's not big. It's not big difference between them, and when it's blue, it's that means that 2.4 it's better than 5.8 gigahertz, and when it's red or orange, that means 5.8 gigahertz is better than 2.4 gigahertz. That shows that changing frequency may be solution for some cases, and we should know when we should use 2.4 and when we should use 5.8 gigahertz. Here we have SINR inside home at 100 megahertz. We can see the difference between this picture and the picture and figure 3. Here we have less frequency than picture 3. With picture 3, and we can see the SINR is better when picture is yellow or red, and it's lower when it's blue. Here we have comparison between using OFDM and we are not using OFDM, and we can see the difference, the place of difference when we using OFDM. When it's orange, that OFDM is better than we are not using OFDM. Here we have a comparison between frequency 5.8 gigahertz and 100 megahertz, and we can see a huge difference between using those two frequencies. As this is different between the figure 5 and this picture in figure 8. You can see here a huge difference. When we're using the 5.8 gigahertz, and it's better than using frequency 100 megahertz. Here we calculate a bit error rate, and we send a random information and receive it to find bit error rate when we're using the OFDM, we're using different modulation cancellation. We can see the QPSK is the lowest bit error rate, and 16 QIM is the second, and 64 is the third, and 256 QAM is the fourth. Conclusion: as we saw, OFDM improved as a SINR and bit error rate inside the building, and it may be a solution for the interference problem. Higher frequency improved the throughput due to limits interference, but the difference between 2.4 and 2.4 gigahertz and 5.8 gigahertz, it's not significant as we see in the figure 5. Multiple antenna are a future subject of study, like we can use directional antenna or intelligence antenna in the future. Thank you for listening. Any question?
Thank you, Azam. So, anyone would like to ask any questions? So I see, Azam and Shoaib, sir, you use similar platform for research.
Or what? I can't answer.
like Shoaib's work also was similar work, but maybe on different applications.
No, with the previous simulation, you mean?
Yeah.
Yeah. We did two papers. We did two papers. The first paper for 3D ray tracing, and second paper we use it to using OFDM and finding SINR everywhere in
Okay.
the
With
home.
different applications. Okay.
No. We using the 3D ray tracing is the same is the same application. It's the same application in MATLAB. We make it in MATLAB.
Okay. Fine.
For two papers.
Okay.
Yeah.
So one is on smart home IoT. Shoaib was talking on, and you were talking on energy efficient, basically.
Yeah. Energy, because when we decrease the interference, we will increase the lifetime of the sensor network, because in wireless sensor network, the power supply in the internal in the network.
Okay.